Could there be an ocean under the Earth? Through global-scale seismic imaging of the Earth's interior, research led by the University of Alabama revealed a layer between the Earth's core and mantle that is likely a thin, dense, sunken ocean floor. But how? Is it possible that there is an ocean under the surface of the Earth? What temperature could it have? Could there be living things in it? Keep watching to find out. Ultra-low speed zones, ULVZ. To better understand this discovery, we must delve into the central topic of the investigation, the ultra-low speed zones, also called ULVZ by their initials. ULVZs are mysterious and fascinating areas under the Earth's crust that have puzzled scientists for decades. These zones lie at the core mantle interface of our planet, at a depth of approximately 2,900 kilometers below the Earth's surface. Unlike the rest of the mantle, which is composed mainly of magnesium and iron silicates, ULVZs have a very different composition. These zones are characterized by their low seismic velocity, which means that seismic waves slow down or even stop completely when they pass through them. This indicates that the density and composition of these structures in the Earth's interior differ significantly from those in the rest of the mantle. One of the most popular theories about their formation is that they are related to subducted materials. Subduction occurs when one tectonic plate dips under another and sinks into the Earth's mantle. The minerals found in these plates can remain stable at very high depths and temperatures, and can therefore be transported to the core mantle interface. These subducted minerals are believed responsible for the density and composition differences that characterize ULVZs. ULVZs have been identified worldwide, suggesting that they are not a local feature, but rather a global feature of the Earth. Furthermore, it is believed that these zones may have significant implications for the dynamics of the Earth's mantle and the planet's evolution. ULVZs cannot be seen since they are underground. So how do we know if they exist if we have never seen them? Scientists have used various techniques to investigate these structures and obtain information about their composition and origin. One of these techniques is seismic tomography, which uses seismic waves to map the Earth's internal structure. Seismic data is combined with theoretical models to build three-dimensional images of the ULVZs. Another technique used is high-pressure and temperature mineralogy. This technique involves high-pressure, high-temperature experiments that help determine the stability of minerals at the depths and temperatures found at the core mantle interface. These experiments provide information about which minerals may be stable under these conditions and form structures in the planet's interior. The study published in the journal Science Advances provided new evidence on the composition of the ULVZ. The study authors used molecular dynamic simulations to examine the stability of various types of minerals. The results suggest that minerals containing iron and silicon, such as ferropericlase, may be stable under these conditions. Therefore, megastructures around the mantle may be formed by these materials. The authors also conducted geochemical analyses of Earth's mantle rocks. They found evidence for the presence of these minerals in the lower mantle, further supporting the theory that ULVZs are composed of subducted materials. The importance of understanding these enormous structures is that they can have significant implications for the dynamics of the Earth's mantle. ULVZs can act as barriers to the material flow in the mantle and affect Earth's interior heat distribution. They may also play an essential role in forming mantle plumes, updrafts of hot material that rise from the mantle to the surface. In addition, it is believed that they may be related to the formation of some of the most mysterious geological features on Earth, such as the famous South Atlantic magnetic anomaly. The South Atlantic magnetic anomaly. It is a geophysical phenomenon that has puzzled scientists for ages. Refers to a region of the South Atlantic Ocean where the Earth's magnetic field is significantly weaker than expected based on geographic location. This region stretches from South America to Africa and has been the subject of intense research and debate among scientists. Earth's magnetic field is produced by moving the liquid iron inner core within the planet. The magnetic field is essential for life on Earth as it shields the planet's atmosphere and surface from solar and cosmic radiation. However, this field is not uniform across the planet and varies based on geographic location. AMAS is one of the most significant magnetic anomalies in the world and is believed to be caused by a combination of several factors. First, the South Atlantic region is known to have a large amount of volcanic and sedimentary rocks rich in iron and other magnetic minerals. These minerals can distort and weaken the Earth's magnetic field in certain areas. Furthermore, it is believed to be related to the Earth's outer core dynamics. The outer core is a layer of liquid iron that surrounds the inner core and is in constant motion. This movement can create electrical currents in the outer core that, in turn, generate Earth's magnetic field. It is believed that these electric currents may be disturbing the magnetic field in the South Atlantic region. In the last decades, geological and geophysical studies have been carried out in the region to understand this anomaly's cause better. One of the most widely used tools in these studies is magnetometry, which measures the strength and direction of the Earth's magnetic field. Scientists have also used satellites to map this area from space. The data collected by these satellites have allowed scientists to create detailed maps of the anomaly and to analyze its distribution and characteristics. As scientists have delved deeper into this region, they have discovered that this anomaly has significant implications for navigation and communication. The weak magnetic field in the South Atlantic region can interfere with compasses and other navigational equipment, which can be dangerous for ships and aircraft traversing the region. Furthermore, this zone of low magnetism can also affect satellite communication and other telecommunication systems. Cosmic radiation penetrating the Earth's atmosphere can be affected by the weak magnetic field in the region, which can cause failures in communication systems. The investigations to study the South Atlantic magnetic anomaly have also helped us better understand our planet's structure. Thanks to this, we have discovered that ultra-low speed zones exist inside the planet. But we have also discovered structures the size of mountains that appear to be ancient oceans. Buried mountains and oceans. Recently, the project led by research fellow Samantha E. Hansen of the Department of Geological Studies, the University of Alabama, conducted seismic wave surveys in the Southern Hemisphere and Antarctica. These provided the highest resolution images of our planet's interior structure, and we've discovered that Earth's internal structures are much more complicated than previously thought. The project was able to probe a large part of the Southern Hemisphere in high resolution for the first time, using a detailed method that examines the echoes of sound waves from the core mantle boundary. Hansen and the international team identified unexpected energy in the seismic data that arrived several seconds after the reflected wave at the boundary. These subtle signals were used to map a variable layer of material across the study region that is pencil thin but several tens of kilometers long, which is somewhat surprising, considered that the Earth's dominant layers are several thousand kilometers thick. The properties of the abnormal lining of the core mantle boundary include substantial reductions in wave velocity. That is, it is made of the same materials as ultra-low velocity zones. These ULVZ discoveries can be well explained by ancient oceanic seafloors sinking to the core mantle boundary due to the sinking process of continental plates. Oceanic material is transported into the planet's interior, where two tectonic plates meet, and one plunges beneath the other, known as subduction zones. Accumulations of subducted oceanic material build up along the core mantle boundary and are pushed by slowly flowing rock in the mantle over geologic time. The distribution and variability of such material explain the range of properties observed. ULVZs can be considered mountains along the core mantle boundary, with heights ranging from less than 3 miles to more than 25 miles. This suggests that below the Earth's surface, around the core, are mountains up to 5 times higher than Mount Everest. That is to say that inside our planet, there are remains of what thousands of years ago was the continental plate that contained oceans as large as the Pacific Ocean and mountains larger than Mount Everest, but are now several thousand kilometers below the surface. But wait, don't let your imagination fly yet. This does not mean that inside our planet there is an internal world like the one Jules Verne imagined in his book Journey to the Center of the Earth. These structures are just ancient remnants from the Earth's surface now found very close to the core at extreme pressures and temperatures of more than 9,000 degrees Fahrenheit, temperatures no living thing could survive. While liquid water or living things can't exist in the Earth's core, these underground mountains may affect how heat escapes from the core, the part of the planet that powers the magnetic field. In addition, material from ancient ocean floors can also become trapped in mantle plumes or hotspots that return to the surface via volcanic eruptions, meaning these structures could eventually end up back on the surface with time, returning to the place where they were initially. Other hypotheses about the origin of these structures inside our planet suggest that they result from the formation of the moon. These hypotheses are based on the theory that the moon originated from the impact of a vast body the size of Mars called Theia, which collided with the Earth 4.5 billion years ago. From that vast impact, much of the Earth's crust was lifted several kilometers into space and then redeposited on Earth, but was buried by the rest of the debris and rocks from the collision. A large part of the scientific community supports this idea, since it would explain why these structures are uniformly distributed throughout the planet and not just in some areas. In addition to the impact of Theia, it also explains why the Earth's axis has that inclination. Although there is no conclusive evidence yet, little by little science brings us closer to finding the truth. Ultimately, research into the Earth's core reminds us of the incredible complexity of our world and how much remains to be discovered. By continuing to explore the secrets of Earth's core, we can better understand our place in the universe and how we can live in harmony with our planet.